Hi, welcome to another episode of Algebra in Words, the video series on YouTube. In this video, we're going to continue our discussion on rational expressions and equations, specifically looking at an example of another rational equation. So anyway, without further ado, let's take a look. So first of all, what I want to point out is this is a rational equation. There's ratios or fractions, or what you know as rational expressions, this and this, in an equation, and it's an equation because there's an equal sign. So the goal is going to be to get a value for x or solving for x. So that being said, now there are other videos where we go over solving rational equations, but this is sort of its own little subcategory, and there's a detail that we want to point out in the beginning. And what that is we want to recognize that there are one fraction on each side of the equal sign. And why does that matter? It matters because of the direction in which we're going to go to solve. Now, when there's one fraction on the left and one fraction on the right, that's kind of good because the method that you can use to solve is going to be faster than doing the method if there were more than two fractions. And in that case, that means we're going to cross multiply. So without further ado, let's get started. What is cross multiplication? Cross multiplying is when you multiply the numerator of the left fraction times the denominator of the right fraction, and vice versa. The denominator of the left fraction times the numerator of the right fraction. So I'm just going to write out what it would be before we actually multiply it, just so you can see the steps in case you're not familiar with cross multiplication. So this times this is going to be 2x times, and I'm putting in parentheses, this 2x plus 1 equals this times this. And again, let's do negative 1 and then parentheses 2x plus 1. So that's this times this, which is here. And now let's just distribute and multiply through where we can. So 2x distributed throughout this, 2x times 2x is 4x squared. And 2x times 1 is 2x. Then on the right, we have negative 1 times 2x, which is negative 2x, and negative 1 times positive 1, which is negative 1. And now let's move everything to one side of the equation, specifically the left side of the equation. And why do I recommend that side? Because you should move all the terms of the equation on the side that has the x squared already, which would be this side. May not seem like a big deal, but if we were to graph this, we would graph it properly by keeping the highest degree term on the side that it started from. So we're going to add 2x and add 1 to both sides to move these terms to the left. Plus 2x plus 1. And now when we combine like terms on the left, we have 4x squared plus 4x plus 1 equals 0. And now that we did that, this is one of the reasons it's important to move everything to one side, is because now that they're on one side, it's in descending order, all the terms are combined with their like terms. Now we can attempt to factor if possible. So let's try to factor. And what if we do 2x plus 1 times 2x plus 1? And let's just FOIL that to make sure that that works. Product of the first is 4x squared. Product of the outside is 2x. Product of the inside is 2x. 2x plus 2x is 4x, which is the middle term at the top. And 1 plus times 1 equals positive 1. So these are the correct factors to use. And now let's set each factor equal to 0 and solve for x. So 2x plus 1 equals 1, minus 1, minus 1. And let me just bring this up here so we have more room. Minus 1, 2x equals negative 1. Divide both sides by coefficient 2. And x appears to equal negative 1/2. But because this is a rational equation, before we circle this, we have to test to see if it's accurate by finding the extraneous solutions. And that means setting each denominator of the fractions equal to 0 and solving. So let's do that. It's a step that I recommend doing in the beginning of the problem, if you remember, but in this case we're doing it after. That's fine as long as you remember to do it. So let's squeeze that in right here. 2x plus 1 equals 0. And you may see where this is going already, but bear with me. So minus 1, 2x equals negative 1. Divide both sides by coefficient 2, which cancels out. And we're left with x equals negative 1 half. X equals negative 1 half. I don't know if you can see that there. So let's just write it up here again. X equals negative 1 half. Now, this was an extraneous solution, so I'm going to put a cross through the equal sign like this, because this x solved came from straight from the denominator. Now, if you remember what an extraneous solution means, it means that your regular solution cannot be the same as an extraneous. And in this case, we see that it is. This was an extraneous. This is what we solved for, or thought we solved for. So we have to cross this out. And because our binomial factors were the same, I don't know if you can see that, because our binomial factors were the same, then the solutions for each one ended up being the same, negative 1 half. So therefore, that's the only solution that we could have possibly had, and the extraneous solution canceled that out. So the answer for this problem is no solution. And that concludes the problem in this example. I'm going to pause the video and put one more problem up. Okay, so I have another problem up on the board, and it's 1 over x minus 1 plus 1 over x plus 1 equals 1 over x squared minus 1. Now, the first thing that we're going to do is set each denominator equal to 0 and solve for x to find the extraneous solutions first. And since this one is x squared minus 1, hopefully you recognize it as the difference of two squares, let's just factor that right here as x minus 1 and x plus 1, conjugate binomials. And now we'll come to the bottom. Let me see where you can see that here, about here. And let's set each denominator equal to 0. So x minus 1 equals 0. That comes from here, and that also happens to be the same as this factor, so it's a duplicate. Plus 1, and we get x equals 1. X equals 1 as our first extraneous solution. Let's put a slash through that, so it means x cannot equal 1. And now let's do the same for x minus, we just did x minus 1. Let's now do x plus 1, which again is a duplicate of this factor, x plus 1. So x plus 1 equals 0, minus 1, and in this case, x equals negative 1, meaning it cannot equal negative 1. So I put a slash through that. All right, so that's that. Now we can kind of start the bulk of the problem up here. So the next thing we're going to do is look for we would want to factor the denominators if we haven't already, but we already have. Also, let's put these in parentheses to recognize them as binomial factors. And now let's go to finding and determining the least common denominator. So let's do that here. Let's just write it out. Least common denominator is going to be the quantity x minus 1 times the quantity x plus 1. That's our LCD. And what are we going to do with the LCD? We're going to multiply that times every term, meaning the numerator of each fraction. So let me change markers so that we can see that. And just so we have a little more room, I'm going to put the 1s here. And now we're going to multiply the numerators of each times the LCD. So here, x minus 1 times x plus 1. Over here, x minus 1 times x plus 1. And here, x minus 1 times x plus 1. 1. We multiplied the least common denominator times every numerator of each fraction. Let's pause there for a second and just remind you why we're only multiplying times the numerators. Multiplying each fraction by the LCD, by default, assuming we determine the LCD correctly, which we did here, is set up so that all of the denominators will cancel out with some factor in the top. And also, it's worth pointing out that this method is different than if we were only adding and subtracting fractions in a rational expression. In a rational expression, long story short, you're multiplying the top and bottom of each fraction by a factor if necessary. But I don't want to go too much into that in this video. I went over that in another video called Adding and Subtracting Rational Expressions. You can check that out to see that method. But before we go back to the problem, it's very important that you distinguish the different methods between solving a rational equation and simplifying and adding and subtracting rational expressions, because the methods are different even though they look very similar. So let's get back to the problem. We multiplied the tops of each fraction by the LCD. And the next step is to cancel out any common factors in the top and bottom of each fraction. In the first one, x minus 1 cancels with x minus 1. In the next fraction, x plus 1 cancels with x plus 1. And in the fraction to the right, both factors x minus 1 and x plus 1 cancel out with the complete bottom, and it's the same as x squared minus 1, it's just that factored is x minus 1 times x plus 1. So so all of these factors cancel out here. Now let's go back to the left and now write whatever factors remain in the numerators, if any. And let me change markers, and we're going to come over this way. So up here, what is left after we canceled that factor out? We have 1 times the quantity x plus 1, and x plus 1 times 1 is just going to be x plus 1. And next we have plus 1 times the quantity x minus 1. X minus 1 times positive 1, make sure you keep the sign with the 1, is just going to be, again, itself, x minus 1, plus x minus 1. Then equals, and then when we come over here, even though all of these factors of the LCD cancel with all the factors in the denominator, we're still left with 1, and don't forget to write the 1. So we're left with 1. Now, let's consolidate all like terms. Since we already know that we have only x to the power of 1 and constants, meaning numbers of like 1, let's move the variables to the left, or they're already there, and move all the other numbers to the right. So, since we have 1 and 1 on the left, I'm going to minus 2, because 1 and 1 is 2, on both sides. That's going to move all the 1's to the right as minus 2, and on the left, x plus x becomes 2x. So we have 2x on the left, 1 minus 2 is negative 1. Now let's divide both sides by coefficient 2. And these cancel out, and we're left with x is equal to negative 1/2. So the question is, before we circle our answer, x equals negative 1/2, can we circle that? Is that a valid answer? Well, to know that, we have to compare this to what we calculated as the extraneous solutions in the beginning. And here we had x is equal to 1, meaning cannot be 1, and negative 1. So does 1 or negative 1 conflict with negative 1/2? No. So by that comparison, we now have validation that our answer, x equals negative 1/2, is sufficient and works. If we wanted to check that, we could take the negative 1/2, substitute it back into the original equation, and even just the denominators, but into the original equation, simplify, and see what it becomes. So anyway, that concludes this video on solving rational equations. To summarize, the first example we did, we were able to just use cross multiplication. We still needed to find the extraneous solution. In the second example, there were 3 fractions, so we could not do cross multiplication. We found the LCD, and we multiplied the LCD times the numerators of each fraction. We canceled out any common factors in the top and bottom, and then we took whatever was left, multiplied if necessary, combined like terms, and then solved for x, which we got. Then we compared x to the extraneous solutions, which came from solving x from the denominators of the original fractions. It's very important that you remember to always set your denominators equal to 0 to find the extraneous solutions first, because it's a step that a lot of people often forget. So anyway, I hope you found this video helpful. If you did, please give a thumbs up, please subscribe to the page, please hit the bell so that you can be alerted when new videos come out, and also if you know anyone that could find this helpful, please share that with them. Also, be sure to check out other content on Facebook and Instagram, and I'll see you in the next video.